Hello, I'm Simon, and I'm presenting our work on mechanized logical relations for termination-insensitive noninterference. Information flow control is about tracking how information gets propagated through a program, making sure that the sensitive information that the program might be computing on is handled securely and not leaked in unintended ways. The usual basic semantic notion of secure information flow is known as noninterference. Intuitively, it means that the publicly observable outputs from a program execution should be independent of the secret inputs given to the program. This is illustrated by the missing arrow from secret input to public output in this diagram. To be more precise, a program E satisfies termination-insensitive noninterference, abbreviated Timany, when given two different secrets, V1 and V2, then running E with either V1 or V2 as input implies that the observable outputs will be equivalent. What observable output means and when they're equivalent, of course, depends on the concrete language that we're considering and the attacker model. Information for control enforcement is often specified using a static type system. Such a type system, types are annotated with labels that denote a security classification, such as public or secret. The type system is set up in such a way such that well-typed programs automatically satisfy the security condition, in our case termination-insensitive noninterference. However, for such a static type system to be useful in practice, it must support the same kind of features as you would expect from a modern programming language. That includes higher types, reference types, polymorphic types, recursive types, and whatnot, that are all essential for implementing reusable software components and modern software engineering practice. The difficulty of proving the type system is sound when we start adding all these features and combining them increases rather drastically, however. This is exactly the gap in the literature that we're addressing with this work. The main goal of this work is to show that such a rich type system satisfies termination-insensitive noninterference. We want to do this using a semantic model and with full mechanization of all our results and examples in the coq-proofer system. Even with a very expressive type system, any static type system is necessarily overly conservative, as illustrated by the need for an unsafe construct in a language like Rust. This entails that there is a large body of programs that cannot be type-checked, while still being, for us, information flow secure for reasons too subtle for the type system to verify. This could be, for example, a low-level implementation of a data structure that's optimized for efficiency, or some system that is governed by security policies that rely on value dependency or dynamic runtime information. What our semantic approach allows us is compositional integration of syntactically well-typed and ill-typed components. To be more precise, if we have an expression E1 that type checks syntactically as type tor1 in a context where X has type tor2, well then given a different expression E2 that might not necessarily syntactically type check, but semantically inhabits our model at type tor2, well then we can, without problems, substitute E2 for X in E1, and the resulting thing will still be secure. To illustrate this concept, I have two, arguably contrived examples, but they still serve as a simple and motivating example. More interesting examples are found at the end of the presentation and in the paper, of course. The first example is a function that takes in a value and multiplies it by 0. Note here that most conventional type systems will not be able to type this function as taking a secret natural number in and outputting a public natural number. The reason is that a binary expression is usually depending on both its operands, and therefore the security classification of the result of the binary operation should also be sensitive in this case. However, due to arithmetic facts, of course, the result of the function is perfectly fine to be considered as a public natural number. And this, in fact, we can prove in our semantic model. The second example I have here uses two references, L for public information and H for sensitive information. The program starts by copying the contents of L into an auxiliary variable X, and then it copies the secret information from H to the public reference L. In most flow-insensitive type systems, this will not be deemed secure, and this would constitute a leak. However, in our concrete case, we're recovering the contents of the publicly observable reference, which means that the program is perfectly semantically secure. Let me continue by fixing the language that we're studying. The language is an ML-like language with a call by value operational semantics. The most interesting part of the language is by far the type system. The types of the language, Tor, consist of an unlabeled type T and a label L. The unlabeled types contain booleans, natural numbers, products, and sums, as you expect, as well as a type of high-order functions. Our type of high-order functions is annotated with a label that we call a latent effect label. The reason is that when we, in some context that depends on the secret information, decide to invoke a function, well, then it's important that the function f, in this case, does not have public side effects, because otherwise we would be leaking secret. That could be, for example, writing to a public reference. For this reason, we keep track of a lower bound of the side effects, the latent effect label, in the type system. Moreover, we have a type of general references, as well as a type for type polymorphic terms. This type polymorphism is a system F style impredicative type polymorphism, where we're quantifying over some, in this case, unlabeled type alpha. As type polymorphic terms are essentially lambdas, they can also have side effects when invoked. And therefore, for the same reason as for ordinary functions, this term we also have a label annotation on this type, denoting a lower bound on the side effects that a function might have when invoked. In a similar spirit, we also have a label polymorphism, quantifying over some label variable kappa, and also with a label annotation for the same reason. We have existential types and recursive types as well. And as we have label polymorphism in our language, our syntactic labels, L, are either label variables or labels from a concrete lattice, or the join of two syntactic labels. For the sake of this presentation, it's perfectly fine to consider a public and secret lattice, two-point lattice, with public and secret top and bottom. The typing judgment says whether an expression E has type tau. It does so in a type level or in a term level context gamma, and in a type level context with the type variables that might occur in gamma or tau. Similarly, it also has a label context psi with label variables that might occur in tau or gamma. Finally, the judgment also has what is called a program counter label, which constitute a lower bound of the side effects that E might have when being evaluated, for similar reasons as for the function type. While I don't want to show you the whole type system, I do want to give you a feel of how the type system looks like by showing you these three rules. The first rule is for typing conditional expressions. And here we're typing a conditional expression where they got E and two branches, E1 and E2, and are type tau. The conditional guard should be an expression of Boolean type with a label L. And moreover, to account for the fact that control flow now depends on L in the branches, we should type the branches with a PC label that is joined with the label L. This judgment to the right simply says that the label of tau should be at least as high as L in the lattice. This is to make sure that the type, when we're typing the conditional, now correctly says that the expression now depends on something of label L. The next rule encodes what I meant by E being a lower bound on the side effects. Oh, sorry, with PC being a lower bound on the side effects. In this case, we're typing writing to a reference E1 with some value E2. E1 is typed as a reference with contents of type tau, and the value E2 that we are going to write to the reference is also of type tau. Crucially, as enforcing the lower bound on side effects, we require that the PC label is lower than the label of tau. It correctly says that you cannot, in high context, write to public references. The final rule I have is for typing type polymorphic terms. In this case, the body of the lambda is typed in a context where the type level context is extended with alpha, and the PC label is going to be the one from the type annotation. Now, this soundness theorem that we claim and prove holds for this type system looks as follows. So it says that given an expression that is typed as a public Boolean in a context where x is a high Boolean, then given two different secrets, v1 and v2, well then if you are either substituting v1 for x or v2 for x, then the resulting values of evaluating these two expressions will be the same. The way we go about proving this theorem is by setting up a binary logic relation. The property that we're interested in is of course binary and is relating to programs. Our relation relates expression E1 and E2 at a type tau. And this relation is set up in such a way such that the syntactic typing judgment implies that the expression that is being typed is being related to itself. This is usually known as the fundamental theorem of logical relations. Moreover, we also show that an expression being in the binary relation implies that the expression doesn't indeed satisfy termination-insensitive noninterference. However, defining such a relation, because we have all these complicated features and a very expressive type system, means that we have to define a rather complex semantic model that includes handling the type wall circularity and things like that. To combat this complexity, what we do is using the separation logic framework IRIS for defining a relation. With IRIS, we have convenient modalities to express a relation, and IRIS has already given us good ways of solving the type wall circularity. What it also means is we can define our relation at a high-level abstraction, and we can use this high-level logic to reason about a relation, both for doing manual proofs about programs and for showing all the theorems around the relation. Finally, IRIS also comes with a coq formalization and IRIS proof mode for mechanizing all our proofs. However, existing works on these logical relations, where using a logic to phrase our a logical relation, are all aimed at proving different kinds of refinements. Intuitively, what it means when we say that E1 refines E2 is that if E1 evaluates to some value V1, then E2 should also evaluate to a value of V2, and these two things should be suitably related according to some relation. However, what we need for our case here is a termination-insensitive notion. That is, if E1 evaluates to V1 and E2 evaluates to V2, then something should be related, or the resulting value should be related. This means that all the existing work on using logical relations, in IRIS in particular, can simply not be used. For this reason, we define a novel theory of modal weakest preconditions, which you can read a lot more about in the paper. While I don't want to give you all the details of the semantic model, I want to give you a high-level idea about some crucial points. A central idea in the model is to interpret types both as a binary relation for relating terms that are publicly equivalent for stating our non-interference intuition, but we also need, in order to define our binary relation, we also need to define a union relation for characterizing terms that do not have public side effects. To see why this is needed, let's consider an expression that simply branches on some secret, V or V prime, and otherwise continues as either E1 and E2 as conditional branches. In terms of our relation, to prove that this conditional is semantically secure and satisfies non-interference, it means that we have to, in terms of our relation, show this judgment, where V and V prime being secret means that these two values can in fact be two different booleans, where we're sort of carrying over the intuition that we saw from the non-interference theorem, saying that execution cannot depend on these secret values. However, what this means when we have to show this is that the execution of the left-hand side and right-hand side might go into two different branches. Crucially, it means that we end up having to prove, among other things, that E1 should be related to E2. But this is in principle two expressions that have nothing to do with each other. However, this is perfectly fine because in this case we have to prove that the resulting value is related as a secret, so it might actually deviate from each other. However, it is crucial that these two expressions may not modify public references. And for this, we need the union relation to capture what is often called the confinement lemma in proofs of non-interference. We need to know that while these two expressions running and executing high branches independently, neither of these two things will modify low-level locations. Next thing I want to show you is the term of semantic typing. So now recall, right, that our syntactic typing judgment implied our logical relation, and our logical relation implied the soundness theorem. But importantly here, the semantic relation is not defined in terms of the syntactic relation. This means that if we have some code that cannot be syntactically typed, but we can actually prove that it inhabits our relation, well, then we can actually also prove that the program is secure. At the same time, given an expression E1 that semantically inhabits our relation at type tor1, depending on some x of type tor2, then given a different expression E2 that also inhabits our relation, we can also compose these two things in the same way as we could for the non-interference theorem. What this means is that E1 might be an expression that actually syntactically type checks and inhabits our relation due to the first implication. But E2 might not necessarily be syntactically well typed, but we can manually prove that this program is secure. A more elaborate example than the one I showed you earlier is the following. Both this example and the following one will be about value-dependent classification. This program takes in a function as input and starts by allocating a reference containing a pair of a Boolean and a secret. The function starts by or continues by invoking the function f with this reference d. It follows by reading the contents of d, and then it branches on the Boolean. If the Boolean is true, then it will return some dummy value, in this case 42, or otherwise it would return v. The crucial observation here is that this program simply does not syntactically type check at a public natural number. The reason is that the type system is simply not capable of seeing the relationship between the Boolean true and the secret in the second projection. The reason is that the program intuitively maintains an invariant that says that if the first projection of the pair is true, then the second projection is secret, and if the first projection is false, then the second projection is public. However, even though our type system cannot see this invariant, there might be hope that we can do this in our model. And yes, ideally, we should be able to prove that the program with well-behaved f functions inhabits our relation. So of course, it relies on f maintaining this invariant that we're talking about. Crucially, we can use the logic, the Aarhus logic, to both express this requirement and prove this concrete example, and we can use the logic to prove that arbitrary f might satisfy the requirements. One caveat with this example, though, is that for any f that we might want to invoke this construct with, we will have to prove something about it. This burdens the client of this function with proof propagation. However, interestingly enough, we can actually exploit this very expressive type system to conceal the proof propagations. In this modified example, what I've done is essentially wrapping the reference that we were talking about before inside of a module, an existential type, with methods for modifying and reading the reference. This means that the invariant that I was talking about before is encapsulated within the module. Again, crucially, it means that without any kind of other requirements, we can now prove that this modified program is related at this existential type. And therefore, it can be composed with any other program that might depend on a value of that type. In summary, what we've done is we've defined a novel semantic model of an expressive information control type system with support for system F style and predicative type polymorphism, label polymorphism, recursive types, and general references. We also showed that this type system does indeed entail termination-insensitive noninterference, and we illustrated through examples how the model can be used to reason about syntactically ill-typed but semantically secure code with a compositional integration of both syntactically well-typed code and secure semantically proven code. Technically, this involved a union and binary logic relation model and a theorem of modal weakest preconditions that you can read more about in the paper. Both the paper and the COG formalization is available online. Feel free to reach out if you have any questions or comment on this work. Thank you for watching.